this is a tutorial for spectral acceleration calculation. So, have you ever wondered about how buildings are designed to withstand earthquakes? The ASCE 716 design response spectrum helps engineers to predict how much shaking structure will experience based on its height, flexibility, and location. In this tutorial, we'll break down key concepts like SDS, ST1, and site classifications, explain the formulas used to calculate the spectral acceleration, and then use Python to generate and extract the response spectrum data. By the end, you'll be able to apply these calculations in seismic design and analysis software like SAP 2000, ETABS, and OpenSees. So let's get started. First, understand this graph here. So we have this response spectrum graph from ASCE 716. It shows how buildings of different heights respond to earthquakes. So there is an x-axis and d seconds represents the structure's natural period, a shorter period for stiff buildings and longer period for flexible high rises. The x-axis is for period and the y-axis is for SA in G, represents the expected acceleration due to seismic forces. For shorter period buildings, T less than TS, acceleration remains constant at SDS. For longer period buildings, TS less than equals to T less than TL, acceleration decreases as 1 by T. And for very long period T greater than TL, acceleration decreases even faster as 1 upon T square. So this graphs helps engineers to design buildings to resist earthquake by estimating the expected forces at different vibration periods. So now let's understand the Python implementation. So here we have imported the libraries for NumPy for numerical calculations and Matplotlib for plotting the graphs and pandas for tabular data that will provide at the end. So we have defined input parameters here. SS and S1 represents the mapped spectral acceleration for seismic hazard maps. So we have SS as 1.0 for short period spectral acceleration and S1 as a 0.6 mapped to 1 second spectral acceleration. Then we have FA and FV. So these are the coefficients, site coefficients that modified the spectral acceleration based on soil conditions. So we have FA for a short period and FV for longer period. Okay, then we have TL, that is a long period transition point, that is 4, and we have T. So we are calculating T based on the period range here with the NumPy function. So it generates the 500 period values from 0.01 second to 5 second for a response spectrum, and here 500 is the generates the 500 different ranges, you can see 500 different points. So here is the function for calculating spectral acceleration. So first we are giving some inputs that we defined earlier, and this function calculates the SA for different periods T based on ASCE 716 equations. So here we are first defining how to calculate SMS and SM1. So these are modified mapped spectral acceleration that include side effects. So how are we calculating it? So it is a simple SMS is FA into SS, as you all know, and for SM1 it is FV into S1. Okay, and now there comes SDS and ST1. So these are design spectral acceleration value adjusted by 2/3 factor which accounts for seismic risk reduction based on the probability of exceeding map accelerations. So that is why we are just defining STS and ST1 from this SMS and SM1. Then we have T0. This is the period when the acceleration start transitioning from linear scaling to constant value. And there is TS. So this mark the transition between the constant spectral acceleration and the decreasing acceleration phase. And then we are creating the array. This is the spectral acceleration array. Values corresponding to each period in T, we are defining this array. So these are just a definition, or you can say we are defining such variables. And now we are creating the for loop. So for loop will assign looping through the period values and assigning SA based on ASCE 716 equations. So here what is happening is for values for every period we are giving if T is less than T0, then we are giving a particular point STS equals to this value, and this represents the spectral acceleration SA is linearly scaled. If it is this condition T, then we are giving the constant value, means the spectral acceleration remains constant at STS. Then we have T as less than TL. For that we are giving the value the spectral acceleration follows an inverse relationship here, and for T is greater than TL, the spectral acceleration follows inverse square relationship, as you can see here. And we are returning this whole array. And now this is just a function to call and will have this value in SA. Now we are creating the graph. So this function will create a graph of spectral acceleration versus the period that we calculated, and we have the X for period and Y for spectral acceleration. And this is just a graph that I've shown earlier. And then we are saving the data in a CSV with the period and spectral acceleration for each point, and we can save it in CSV, we can save it as a text format as well. So let me show you. It will be saved here as well, and you can download the data as well. For a particular period we have a spectral acceleration. So yes, that's it for the video. Thank you.